So you're still in Taiwan, Junze?
Yeah,
The
I'm
person you are
still.
trying to reach is currently unavailable. Please.
Maybe it's okay. Maybe we can just go ahead. Yeah.
Yeah,
Maybe
I'll just leave him a message.
Yeah, leave him a message. Yeah, okay. Sounds good. Okay. Yeah, why don't you go ahead, Junze? Yeah, please.
Okay. So my name is Junze Li, and today I'm going to introduce the message passing neural states. And we will use this many-body wave function to solve the electron gas with attractive potential.
Mhm.
So first we'll introduce the objective for us to using the neural network, and we'll talk about the theoretical backgrounds, and then we'll introduce special types of graph neural network called a message passing neural network. And the last we'll talk about experimental results.
Mhm.
So to start, we want to discuss the Drexel-Bethel-Verson wave functions. And we know that the stated determinants can be the wave functions of non-interacting Hamiltonians, and this type of wave function did not consider the many-body correlation between particles, and then this can be solved by introduce the Drexel-Bethel wave functions, and then we introduce the many-body correlations through the Drexel factors and the Bethel transformation. And we can think of the message passing neural networks kinds of tools to generate these Bethel transformations and the Drexel terms. And the Drexel-Bethel answers can actually derive from the imaginary time evolutions. And this we know that if the imaginary time, as the time approach to infinities, this imaginary time propagator can project our initial states to the many-body ground states. And the second equality, we insert the identities, and we see that this is the initial wave functions, and this is the imaginary time Green's functions. And then in the last equality, we introduce the average point representation of these integrations. This is actually the average of this integration. The g of gxy sinus y is the average of these integrations. So the whole integration can be written as the volume times the average.
Sorry, y is some particular configuration.
This is
Wow.
kind of coordinates that represent the average of these whole integrations. And we can take an example in the next slide.
I'm just trying to say, can you go to the previous slide? I mean,
yes.
The the part you colored in yellow, right? The right hand side does not depend on y. The left hand side depends on y, right? So I wonder.
Yes, this y is depends on x. So this is kinds of transformations. That's
I see. You can just rewrite that whole thing as
yeah. This is just
okay.
average
So
of
y is
this
a functional of x. So that's
Y
the
is a function of x.
Yes.
Okay.
So this is
You can
just
think of that fine. Okay. You're basically writing the right hand side, right? The
yes.
right hand side is something that depends on x, and you can then divide. Let's see. You want to write it as a product of two parts, right? Well, that's what you want to do. The right hand side, you want to write it as a product of g times phi naught. And g is I mean g is known, right? G is G is
The many body Green's
function.
function. Yeah.
Green's function. G is, you cannot negotiate with G, but you can choose some y so that phi naught is also given, right?
Yes.
So phi naught is given, and G is in principle exact quantity, right? So many-body Green's function.
Right.
So you're saying the right hand side, which is depends on x, you can always choose an y such that gxy times phi naught of y is equal to the right hand side.
Yes.
Mhm.
That's
Yeah,
sort of
exactly.
Okay.
Yes.
So is there a reference about this, the rigorous derivation of gestural?
Yeah, I think it's not, but I think
It's
as
mentioned
your
in the
statement is-
RMP it's mentioned in RMP there's an RMP on the Monte Carlo by I think can't remember, I think David Sepley and David Mayan. It's a fairly common concept in diffusion
Maybe
Monte
you can
Carlo.
send some references to us. Yeah, I mean
Yeah, okay.
after the presentation, right? You know, when you share the slides with all of us, just like what Max and Catch did last time, and then in the new PowerPoint, please give a reference on the
Okay.
slides.
Sure.
Okay.
Sure.
Okay.
Yeah.
Sounds good.
So yeah, here's a 1D example. Yeah. So the G times of psi naught is a function of x prime. And this curve is actually different if we have different kinds of x. And we can think that y is a coordinate that represents the average of these integrations. Since the integration is to calculate the surface under the area under this curve. And the y of x is a coordinate that if we substitute into g times psi naught, and this will be the average of these integrations. And we will call this the backflow coordinate.
Very good. So okay. So let me understand. Can you then go back to the previous slide? So
Yeah.
what you are saying is that the earlier slide.
Previous slide.
Okay. So you're saying that so you're saying basically any many-body ground state wave function, right? Phi, because
Yes.
if tau is large enough, right? If tau is large enough, then
Yes.
the phi tau of x is just the ground state wave function,
Yes.
right? And you're saying the ground state wave function can always be written as phi naught of y times the exact Green's function,
Yes.
right? I see. Okay. All right. Sounds
Yes.
good.
No,
Yeah.
with the condition that phi naught has some finite overlap with the with the exact wave function. I mean, if you go through some phase transition, then you're screwed. But other than that, basically it's you have to start from some mean field type or phi naught, then you can evolve to the exact ground state. That's otherwise I think I don't think you can evolve through a phase transition.
Yeah.
I think phi naught and phi, as long as the same global quantum number, maybe as a matter of principle, they can always write it this way.
Right, but if you break, but if you break some some symmetry like
Yeah, I agree
translational
with you. I
symmetry.
agree with you. Yeah. I mean, it has to be in the same quantum number sector. Right? Yeah.
Right.
Yeah. Okay. Very good. Yeah.
Yeah. So from the previous slides, we know that we can always find a transformation y of x such that the many-body ground state wave functions can be written as the volume times the average of the integrations. And then we can write this term volume times the Green's functions as e to the j of x. And then we can derive our gestural backflow variational form. And so this is just the gestural backflow variational form is kind of another way to write down the imaginary time wave functions. And this backflow coordinates is actually incorporate the information from other electron coordinates. Thereby, this can actually encode many body correlations between other particles.
Very good. Yeah.
Yeah. So now we want to discuss the symmetry of the backflow transformation. And we know that if we have many body wave functions, this wave function need to satisfy the Fermionic statistics such that if we exchange the coordinates of two particles, we will pick up the minus sign. And for example, if we have the permutation matrix like in this example, and we permute the coordinate of the first and fourth electrons, and this will pick up some minus sign of the wave function. And this constraints actually makes us to require the backflow transformations and the gestural vector to be permutation equivariance and permutation invariance. So what is permutation equivariance? Permutation equivariance means that if you permute your input features, the output is also permuted. And the permutation invariance means that if you permute your inputs, the output is invariant. And we can see that if we substitute the definitions of Jesel backflow ansatz into this permuted coordinates, and we know that if the Jesel factor is permutation invariance, and the backflow transformation is permutation equivariance. And in this terms, this is just the stator tenorments with permuted particle coordinates. So this will pick up a minus sign in the wave functions. And this term is actually the Jesel backflow wave functions. So that this
Yeah, very good.
term will
Just to
pick
make
up a
sure,
minus.
when you say permutation, the many-body wave function doesn't necessarily pick a minus sign, right? It depends on how many particles you have permuted, right?
Yeah.
The many wave
Just,
function does not necessarily have to pick a minus sign.
Here he's just swapping two of them. He's just using the simple example.
Yeah, you're just using a simple example. Okay, fine.
Yeah. In this case, we just swap to electrons.
Swap. Yeah, it's not. It's really swapping. Yeah. Okay. Yeah. Fine.
Yeah.
Swap.
Yeah. So we know that in order to satisfy the fermionic statistics, the backflow transformation needs to be permutation equivariance, and the Jesel factor needs to be permutation invariant.
Yeah. Very good. Yeah.
Yeah. So the motivations for us to use the graph neural networks is actually because these two kinds of symmetry is related to the symmetry of a graph. So this can be think of two black blocks. The MPN, the message passing neural network, can be think of two black blocks to generate these two kinds of backflow transformations.
Yeah. Okay, very good. Now, let me ask you a question. Right. Is there something like a universal approximation theorem that says all permutation equivariant functions y of x can be generated this way by graph neural network? Is there some universal representation theorem?
Yeah, I think so.
I think I don't know. James, I think the reverse statement is definitely true. All graph neural networks an attention mechanism can be permutation equivariant.
Fine.
But can
But I think,
graph can graph generate all permutation equivariant?
Yeah.
I think the simple. Or I guess okay. Then I guess I would say you use graph neural networks to generate all your permutation equivariance transformations, and then you feed the graph neural network output into feed forward neural networks. The FNN have a universal approximation theorem. So stack one on top of the other. Then I think we can say that it's rigorous to say that GNN plus some FNN is universal.
Sorry, I'm lost.
So feed forward neural networks have this universal function approximation
No.
theorem.
I think we're talking about y of x, right?
Yes.
The question is, x is, let's say I have n particles. X is n is a vector with n entry elements, right? And y is also a vector with n elements. But you are finding a mapping from x to y such that they are permutation equivariant. The question is, are all such maps can always be obtained from a graph neural network? All possible such mappings. Is that obvious?
Yeah, I think it's not very obvious, but I think some types of function is universally approximate can be universally approximated by neural networks, and I think the graph neural network is just the composition of these types of functions. So I think it's reasonable to think that this type
I
of
think it'd be nice to think about whether there's it'd be nice if there's a proof. Yeah, Tony, do you want to say something?
I have a question though, maybe like just a little bit away from a little bit, but like I think basically you say that the y-axis is like a functional form that you can find such that G, the green function xy times y times phi y, gives you something like the integral, right? But what I wonder is yx unique here? Like, is there, because it seems to me that because G also depends on y, so like it could be that there are many different y's that give you this integral, right?
Good point.
Yeah, that's a good point. Yeah. So it may not be unique. Yeah.
But I mean,
mean-
it's probably good for neural network if it's not unique. Then you just need to learn one of them.
Yeah.
Wait,
probably
but no, but you're integrating over x, x prime. So if you take each slice of x, and then you look at each slice of x prime, then for each x prime, you have a well-defined value for your Riemann area, right? So I would so that the y for each x should be unique.
Wait,
So I
wait,
would
I'm
because
not
you're integrating.
very convinced because it doesn't depend on x prime. Wait,
No, you're
Junza, could you
integrating over
like
x
two
prime.
slides or just the integration? Yeah, this bit. So if you look at the yellow bit, right? It doesn't matter what x prime is. Like, just look at I mean, the right hand side is just a function of x, and then you
Right.
want to take a y such that this left hand side gives you the same thing. But if you pick different y, like, I don't see why it couldn't give you the same thing. Like,
No,
it
so
depends on the G and phi naught, right? It depends on
Yeah.
the property of G and phi naught. Maybe what for some G and for some phi naught, there exists multiple Y, so that the product of G times phi naught can give you the right hand side. That could be right.
yeah, it could be. Yeah.
Could be, yeah. Yeah, these are all very good questions. Yeah.
Mm.
Yeah, go ahead. Yeah.
Okay.
Yeah, I think it's fine. Yeah, please think about this. You know, whether there's some universal representation theorem. Okay. Yeah, please. Yeah.
Okay, sure. Yeah. So now we want to like introduce the graph structures. So the graph is a data structures that consists of the set of vertices V and the edges E. And the nodes of the graph is actually a kind of set, so they are not assumed to be in any ordering. Therefore, if we have two isomorphic graphs, we expect to get the same outputs for the operations that takes the graph as an input. Yeah. So when
Well,
tackling
what do you mean isomorphic graphs? Two isomorphic graphs.
yeah, here's some two example of the graph. Their connectivity is the same, but they are like in different. We can define
Orientation.
this graph to this one. Yeah, they are the same. Yeah.
Wait. Are you saying that for graph you don't care about the? I see. But wait, you're not. Yeah, you're not thinking about graph as a. So all you care is connectivity. Is that what you mean? That
Yeah. All we care is their connectivity. We don't care about the labeling of the nodes.
But also, you
We
don't
only
care about the
care about-
position of the nodes, XY coordinates.
The XY coordinates is, I think the XY coordinate is not related to the connectivity of the graph.
Yeah.
Uh,
So you
yeah.
only care about topology of the graph, so to speak.
Yeah, you
In
can
other
say
words,
that.
In other words, all you care is just there are n nodes, and let's say these nodes are connected in certain ways.
Yeah. We only care about this. Yeah.
Some nodes is connected to some other nodes. That's all you care. Okay.
Yeah.
Actually, could you remind me? So in terms of the adjacency matrix, what does isomorphism mean?
Good question.
That's a good question.
I
I
don't
think
remember.
you can think about that if you have a particular ordering of the nodes, if the graphs are isomorphic, you can find a permutation matrix that's X on the adjacent matrix. They are
Yeah.
they are similar by a permutation matrix. Yeah.
I see.
So by this definition, graph is permutation invariant, right?
Yeah,
A graph is a structure that is permutation symmetric,
yes.
so to
Yeah.
speak. Yeah.
So when we are dealing with this problem, like involving the graph, we must enforce our neural network to satisfy the graph symmetries. So this is an example that demonstrates the representation of a graph as an input of graph neural network. And typically, we will write our nodes and our edges as an embedding vectors. For example, if we have a social network, we might represent our vertices as edges, hobbies, or genders, and the edges may be the
very
relations
good.
of different people, and we may think that if they are colleagues, they are friends, or they are classmates. And in our many-body systems, this vertice can be represented by the particle coordinates, their spin or their quantum numbers, and the edges may be represented by their coordinate difference, their spin product, and so on. This is example. So this embedding vectors depends on your problem. So the graph neural network is a kind of transformations that preserve the attributes of the graph symmetries. And this transformation only alters the embedding vectors of the vertices and edges. For example, in this case, the graph neural network only transform the embedding vectors Vi and Eij into Vi t plus 1 and Eij t plus 1. And the graph connectivity is not changed by this GNN layers. And now we want to discuss a special type of graph neural network called message passing neural network. And for message passing layers, we need to define two types of operations. The first one is to aggregate the messages from neighboring nodes, and the second one is to update the node embedding from the aggregated message. So basically, if we want to calculate the message from the node I, we will find their node embedding vectors as well as their edges that links these two vertices as an input. And then we will aggregate all these messages from our neighboring nodes, and then we use this message to update our nodes embedding vectors. So this is a graphical illustrations of this idea. So basically, if we want to update the information of V2, and we will calculate the message from 1 to nodes and 2, 3, 2, 4, and 2, 5. So we can calculate all the message from these pairs of nodes. And then we will aggregate all this message and then use this message to update the informations of this vertex And now we are going to discuss how we construct the nodes and edge embedding vectors. So in this case, we have two types of features. The first type of feature is an initial features that we obtain from the physical systems. And the second one is the hidden states or hidden features that will not depend on the physical system. They are learnable.
Are these are hidden states? These are just parameters, just the variational parameters?
Yeah, they are variational parameters. They are,
okay.
Yeah. So the node and edge embedding is simply given by the concatenations of the initial features and the hidden features. Yeah. And the message function we discussed in the previous slides in MP-NQS is actually based upon the attention mechanism. So what is a attention layers. Attention layers is their outputs of embedding vectors can consider all the correlations of different pairs of embedding vectors as an input. Yeah, so the outputs can consider all the pair informations between all the embedding vectors. And to consider
sorry,
all
can you repeat the
correlations.
slide? Sorry, I'm a little
Yeah.
bit confused. What is so so attention is introduced in what? In the message function?
Yeah. So the message function m of t is
Uh-huh.
is realized by the attention, self
By the
attention.
Okay, all
Yeah.
right, self-attention. Okay, yeah.
So to calculate the correlations between different pairs of embedding, we can sort of think of a ways to calculate we can give them a score to indicate their correlations between these pairs of embeddings. And there are basically two ways of defining these two attention score. The first one is the dot product attentions, and the second one is additive attentions. And the dot product attention is very simple. We basically need two types of transformation, WQ and WKs. And this can generate the query and key of the first feature and the second features. And then we do the dot product of the query and key features, and then we can obtain our dot product attention score. And the additive attention is the same. We just add the query and key of the first and second features, and then pass them through hyperbolic tangents activations, and then pass them through a linear transformation to reduce the dimension to 1, so that we have the additive attention score. And in most cases, people use the dot product attention since they are very fast and the computation resource is much is less than additive attention. So people are using dot product attention. Yeah. So if we draw all the feature out, and we can see that if we want to calculate the correlation between the feature of the first features and other features, we will generate the query of these features and do the dot product between the query and key between other features. And then we can obtain our attention score. And we also need to calculate the attention score of A1 itself, so that we can obtain 4 attention score. And then we will pass this through softbank activations to do a normalization of this attention score. Yeah. So the last procedure of attention layers is to generate features called the values, and then the outputs of these features is actually the sum of these values features weighted by the attention score. Yeah, so this is what we call the attention layer. Yeah, and in previous slide, we see that the attention mechanism is quite complicated, but if we write them in a matrix form, this can be simplified a lot. Yeah. So basically, we concatenate all the input features as a matrix of X. And then we have our linear transformation, WQ, WK, and WV. And then if we tie the linear transformation to our initial feature, we can generate our query key and value matrix.
Wait, sorry, can I have a question, please?
Yeah.
Yeah, so from what I saw here, I feel like the attention mechanism here is like exactly the same as what Cyphermer did, basically, like line to line is So
Yeah,
is it the main difference is kind of just between different layers? You use some sort of graph mapping, but I guess Cyphermer use something different.
Yeah.
Because it seems like within the layer it's literally the same.
Yeah.
So
yeah,
That's
they are
right. Yeah, that's right. Cyphermer, yeah.
Yeah.
It's just
So
that. It's
yeah,
just
let me understand.
that.
Yeah, let me understand. So sort of attention is what is used to propagate from one layer to the other layer. Is that the idea?
No, it's
Yeah,
within. Wait, actually, I
No,
think
no,
I think it's within the layer actually.
No. It creates the messages within each layer, and then
Yeah.
the messages are used to update to the features to the next layer.
But the way
Ah.
you update next layer, it depends on your network. Well, my point is, I think, I guess it also depends on how you call layers, but I think attention mechanism takes in the input within the layer and then gives the outputs within that layer.
Right.
Uh-huh.
And then it uses the output of the attention as a message to update the features to the next layer.
Okay, fine.
No.
I mean, in the precise formula, right? I guess what Catch and Max talked about last time. Are you there, Catch? Huh? So in precise formula, is attention used to propagate from one layer to the next layer, or what is MLP layer? Remind me.
I'm not, no, I think
MLP is just a matrix. It's just a matrix times the input from the previous layer. It's just they call it feed forward. It's just a feed forward neural network. It's multi-layer perceptron. It's you just take a simple matrix and you multiply, and then you get the next value. That's all.
So Tony, you want to say something?
yeah, I think what Cyphermer did is, I mean, this whole self-attention mechanism is within. You can imagine basically you have different steps when you go from one layer to another. The first step is when you take in the input of layer L, and then you want to produce the output of this layer L, and this step is done by attention, self-attention, at least in Cyphermer, and then from the output of layer L to the input of layer L+1. There is an additional step that could either be done, for example, in Cyphermer, is a tanh function plus a linear transformation, which is
Very good.
called MLP.
Very good. Very good. Yeah.
And then in this case, I think in their case, it's a little bit different because they have different
It's using message
connectivity.
passing.
Yeah.
Yeah. Very good. Yeah. So I think that is what I'm looking for. The answer I'm looking for. Each layer has an input and output, right? And the output of L layer becomes the input to the L+1 layer. But before you directly feeds into that input, you maybe need some nonlinear activation function, something like that.
Yeah.
Okay, sounds good.
Yeah. So the query key and value features can be derived from this input matrix times the linear transformation. Yeah. So the attention scores is the softmax of the query and key star products. And this can be written as a matrix multiplications of Q tensor times K divided by the square root of D. And the square root of D is a kind of normalization to avoid the gradient vanishing problems. Yeah. So, and the linear combination in the last layers can be written of this kinds of attention score matrix times the value matrix. Yeah. So the wholesale attention can be written as this form. It's quite simple.
Just to point out here, so since the previous slide, yeah. So Q transpose times K is permutation invariant because if you permute, then the rows of Q transpose switch and the columns of K switch. So Q transpose times K becomes permutation invariant. Then the linear combination X of T plus 1 will be Q transpose times K times V, and V itself was the columns of V will switch. So X is permutation equivalent. That's how this attention mechanism gives you permutation, invariance, and equivariance.
Okay,
Okay, you can just move. Yeah.
that's good. Yeah. So in message passing neural networks, they use different types of attention. They call particle attentions, and basically we
All right, this is particle attention in the neural network community, nothing to do with physics,
I
or is
don't.
it specifically for neural quantum states?
Yeah, they call them the particle attention because they are like summing. They
No, my
are
question is,
summing.
I mean,
Yeah.
when people use the word particle attention, are they referring to neural network application in physics, or are they just in general in neural network for CS for computer science?
I think it's particular for physics.
For physics,
For
okay, fine.
neural quantum states. Yeah.
Okay, fine, that's fine.
Yeah. So the
Yeah, I think in general, when you guys describe all this neural network stuff, it's important to distinguish which aspect is general, is originally developed, let's say, for large languages, for images, and which aspect of it is specifically for physics applications. It
yeah
will be very important to distinguish the two.
yeah.
Okay.
Okay.
So,
Yeah.
so attention was developed by that's general, and then the particle attention is a
It's
a
specific for
specialization.
physics. Yeah.
Yeah,
But then the title of the slides, it should be messenger passing neural network, for quantum something.
Right. Okay. Right.
Yeah,
Okay.
Yeah. Because now you're talking about specifically physics. Yeah.
Right. Okay.
Okay, all right.
Yeah. So the query and key matrix is the
Yeah, I
same.
mean, if you talk about physics, the zeros order question is what are the input initial information to the nodes and to the messages, right? The initial features. What are
Yes.
these?
I will discuss the initial
Later?
feature later slide. Yeah.
All right. Okay. Okay. Because if you don't tell us what is even the initial feature, it's a bit
Yeah,
hard
yeah.
to understand what
Yeah,
It's
query means.
basically just basically electron position and
Yeah, why don't we first
SI
talk about that? Is it okay if we first talk about that and then we can come back to
yeah,
this
yeah.
stuff?
We can talk about it. Yeah.
Yeah.
Yeah. For
Yeah,
example,
exactly. We should come back to examples more. Yeah. Yeah.
Yeah,
Whenever you give a presentation, right, you have to think about the audience, right? If you talk about
Okay.
abstract things for too long, people would get lost.
Yeah. So let me remind everyone about the features we are using. Yeah. So we have two types of feature. The first one is our initial feature that depends on the physical system, and the other one is the learnable hidden states. And the nodes and edge embedding vector is just a concatenation of the initial feature and the hidden states. So we're going to discuss how we derive the initial features. Yeah. For example, if we want to study the homogeneous electron gas, typically we will choose the plane wave orbitals as our single particle orbitals in the stator determinants. And then the initial features of this problem, we will consider some symmetry and the periodic boundary conditions on these problems. For example, the homogeneous electron gas has the translational symmetries, so that the features can only depend on the coordinate difference. And it also have the spin inversion symmetries. So the features can only depend on the product of spin. And the last one is we have the periodic boundary conditions. So the features relate to coordinates should be periodic. Yeah. So in order to satisfy the first two conditions, we can see that our vertex embeddings cannot depend on the particle coordinates and the particle spin. So it is just a learnable embedding vectors. It cannot depend on any property of the particles quantum numbers. And the edge embedding vectors can depend on the coordinate difference. So the RJ here is the RI positions minus RJ positions. And And we also need to satisfy the periodic boundary conditions. So we can use the sine and cosine surrogates instead of this Rij feature. And
So what is the
we
second
also,
term? Yeah, what is the second term? Sine pi over L Rij. What is that for? Oh, this is for the
yeah,
distance.
it's for distance. Since we cannot depend on any Rij, we can only depend on its periodic surrogates. Yeah.
Actually, sorry. In some sense, this is, I guess, this is already captured by the first term. But the thing is, if you want to capture the cusp condition, right? Cusp condition depends on the Rij absolute value, right?
Yes.
That's why you want to do this, because the first term, sine 2 pi over L Rij, that already, I mean, if you know the first term, you should also know the second term, right? The first term in bracket,
Mhm.
Yeah,
right?
yeah.
But the
Yeah.
first term uniquely determines Rij, right, up to a periodicity, right?
Mhm.
So if the first term is known, the second term, the absolute value of that term is also known, right?
Yeah.
I think the only reason that you want to do this is because you want to sort of give a function that give a quantity that only depends on absolute value. That is difficult to learn otherwise. The cusp condition, yeah.
Yeah,
Uh,
maybe this is more easy for the neural networks to learn the wave function if
Cusp,
we
yeah, learn the cusp, yeah.
yeah. And the last feature is the swing product. So we
No,
have
before we go to all that, at the end of the day, all this is for the gesture, right? You're still going to multiply it by phi naught, right? Phi naught, which is just a state determinant.
yes.
Do I understand that correctly? That at the end of the day, your wave function is whatever neural network gives you times the single determinant, which is a determinant of plane waves.
No,
Yes.
the plane wave will have an input of the plane wave will have an input of the y of x, which is the backflow coordinate.
Yeah.
So the Slater determinant.
But in the end, there's still a single determinant. Yeah. It's determined of a phi I. It's not a phi I of x, but a phi I of y of x. Right.
Yes.
Yeah.
Phi I is still a plane wave function.
Yeah.
Yes.
Okay, fine, that's fine.
Yeah.
Yeah, but then let me send this. Then I'm a little confused. If you use that structure in the end, why you say that xi is independent of I'm trying to say, if you think about a non-interacting problem, right? Let's ask a non-interacting case, right? In a non-interacting case, what do you expect? You expect y of x is just
just x.
well, let's be more careful. I think, I mean, if you go back to the very beginning, your actual wave function, in its gestural form, determinant, there's determinant. Yeah, let's look at this more carefully. Yeah. Okay. So okay, the gestural backflow wave function is determinant of phi mu y of x, right? But let's be a little careful. So if I'm a non-interacting case, j is obviously 0, right?
Yes.
Mhm.
And the phi mu y of x, what it should be. I mean, y of x is not just one function, right? It's a set of functions, right? Because it's not just you not only output one y, right? Right.
Yes. Yes.
So I think for the non-interacting case, then you expect that y1, yeah, as you wrote below,
So
y1,
yi will be
Yeah.
xi. That's all.
exactly, yi of x would be equal to xi, right?
Yeah.
I mean, let me be
Yeah.
more specific. Yi of whole x is equal to xi, right?
Right.
Now, in that case, yeah, okay, that is obviously permutation symmetric because yi equal xi. So if you permute x, right, you also permute output y. Okay, fine.
Mm.
Okay, yi is equal to xi.
Mhm.
Now, you sure that your neural network can learn that? Yi equal xi?
Initially we
So
we
my
will
question is that the way you do this, right? You never give any your input, right? If you now go back to the last slide you just went through. Yeah. So we agree for non-intending case, yi should be equal to xi. And now in this case, your input xi naught is just a learnable embedding vector, and your
Yes.
xij is only dependent on interparallel distance.
Yes.
So is it obvious that your neural network can learn yi equal xi?
Yeah, actually, our starting point is like a weekly perturbed Fermi gas.
Yeah, but it's very tricky. If you cannot learn a non-intending case, I kind of don't believe it. I mean, I agree this gestural thing could work because yi equal xi is a perfectly permutation symmetric thing,
Yeah.
permutation equivariant thing, right? That I have no problem with. But for this particular input feature, right, initial feature,
Yes.
xi0 is basically just completely embedding vector. Know nothing about the physical system. All the information about system is containing xij.
Yes.
So in this case, it's not quite obvious. You can actually, you see what I'm saying, right?
So if
Yeah.
it's plane wave, then it'll be it'll be e to the I k xi times k1 xi k2.
No, but that part is
xj.
containing phi. That part is containing phi. Phi I
Right.
xi is e to the I ki xi.
Right.
No, phi I is okay. Let's be careful. Okay, phi I. Yeah, I think phi I. Let me be more specific, right? Phi I xj should be e to the I ki times xj, right?
Right.
And we still expect y of x, yj of x is just xj. Or
Yes, yj of xj, yj of x of all of the x's should be equals to xj.
yeah, I think one has to be a little bit careful all this stuff. So one question is, in the end, you're using a phi. You're still using a set of phi, right? If you go to initial gestural function again, there's
Yes.
a. Can you go back to the very? Sorry, I keep asking to go to the very beginning when you write down the back gestural wave function.
Yes.
No, go to the previous slide.
Previous slide.
Yeah, okay, this one, yeah. Right. So you have phi mu, yeah. Phi mu y j x, right? So at the end
Yes.
of the day, you also input a set of functions phi mu. Phi mu is phi mu is e to the I k mu times y.
Y, right.
That information is provided explicitly, right? So what I'm trying to say that, when you do this gestural backflow, you are using a set of orbitals, phi. Phi is an orbital, right?
Yes.
That information is given to the neural network, or is it learned as well?
We are given the orbitals. Yeah.
Right. Yeah, phi mu is just plane wave orbital, right? You are giving
Yeah.
that's given to the neural network, right? Yeah, so that's
This
fine.
is
In that case, I will say in the non-intended case, y of x, yi of x is just xi,
Yes.
right?
Yes.
So it's not clear that if you use your it's highly non-obvious, right? If you use your initial feature that way, will the neural network be able to learn this thing y I x is just equal to xi? You see what I'm saying?
Because there is no xi input, it's all just xij.
Exactly.
But
Yeah.
But I would guess that when you write out the Slater determinant for the free plane waves, it should respect translational symmetry, right? So it should end
No, I
up being
understand. But your structure is still based on individual orbitals, phi mu, right?
right.
Yeah.
So
So
what I'm saying is, I think e to the I k mu of e to I k mu of y1 or rather x1 and e to the I k gamma of xj, you use all these k mu and k mu1, k mu2 to construct your Slater determinant. It should end up in a form that's probably like, I guess, e to the I k mu xi minus xj.
yeah, no, I think I agree with you. We know that if you take a Slater determinant state, right, it is it's sort of under translation symmetry. At most it pick up phase factor. I think I agree with you on that. You know, any state determined wave function with plane wave basis is translationally invariant, or
Periodic.
at least the
Right.
Brownstein density translation invariant, right?
Right.
I think I mean I agree with that, but it's not clear to me that your neural wave function, this particular initial input feature, you know, from this initial input feature, you can learn the final ansatz, the final answer, which is y ix just xi in non-entangled
Yeah,
case.
I think the
Mm-hmm.
yi has some information of xi. I can show you in a later slide.
So you think it can learn that? With this particular,
Actually,
you know, implementation, you can learn that.
yeah, we actually learned the delta of x is
Oh, yeah.
actually
No, but
yi.
before you learn the delta, I mean, my
Yeah.
question is that can you learn that y in a non-entangled case, can you learn that yi of x is just xi? It's not
But
obvious to me.
what Jinze is saying is that MPNQS, what MPNQS implements is this delta of xi. So
Oh, so
I
you're saying in
think
the
that,
end you add by hand. You're saying you add by hand to it some yi is xi plus delta xi. Is that what you mean?
Yeah,
uh,
MNQS just learned the delta of xi.
Okay. You're saying there is an initial yi equal xi.
And initially we like let the delta xi very small, so that we are starting from the perturbed Fermi gas.
Okay, because you're saying there's the initial input, which is there's additional step, which is you know you write yi is equal to xi plus delta xi,
Yeah.
and the neural network is only used to generate delta xi.
Yes.
Okay, fine. Okay.
yeah, but that's a very good point. Thanks, Fulian. Let me we'll go back and check the implementation more.
Yeah,
a
you
bit more
should check the
carefully.
implementation. Yeah. Is it really the case
Yeah,
that
but
you're using neural net only to generate delta xi, or you're using neural net to generate the whole thing?
yeah.
If you want to use neural net to
Yeah.
generate the whole thing, it looks worrisome to me. Yeah.
Right. Okay. Thanks. Yeah, but
Yeah,
I think
but you know,
in the
but
paper,
let me put it this way. Yeah, if you use neural net to generate delta xi, then it's not obvious to me that the input feature should be
random.
completely you know, because you
Yeah,
are
I
already
know.
focusing on
There's
eyes,
some,
right?
there's some. It seems that there's some conflict there. So yeah, their paper is a
Yeah,
bit.
if you're using if you're using neural net to generate yi minus xi, then the I is obviously special, right? Not all particles are equivalent anymore, right?
Right.
So all these things, you know, has to be completely thought through. You know, when you do research, you always have to start with the simplest thing, right? Just think about the non-entangled case first, right? Before you do anything complicated. Otherwise, one is easy to be fooled, right? Especially with all this neural network, it looks like there's 100 different layers, right? But you always have to think of the simplest thing first. Okay.
Yeah.
Right?
Actually, I just found it really interesting though, because when I read the paper like Google had about quantum phase transition, like the first time they implemented the periodic boundary condition, they actually discussed this thing like whether you should use x and the relative coordinates, so whether you should use both of them, and then they basically say that in this case, in their case, it's like using both gives better convergence than using like RIJ, even if the information about RIJ should be sufficient. That's kind of what they say in the paper, I think.
It's very tricky,
Which
you know.
paper?
I think it's very tricky
Okay.
because yeah, I think on the one hand we agree that the many-body wave function is translationally invariant up to a phase factor, right? So
Yes.
you might think that we should be able to write everything in terms just RIJ, right? On the other hand, you do know in the non-entangled case, right, the wave function is written in terms of a determinant. In the determinant, what enters is unity kx, not xij, right? It's xi, right? So it's very non-trivial. It's very non-trivial. This is very non-trivial, you know.
Yeah. Okay.
One has to really think very
You'll be
carefully.
more careful. Yeah. We have to.
Think very carefully. There's a lot of physics, containing this. Yeah. So it is a miracle in a sense, right? That the slit determinant, even though it's written in terms of one particle coordinate, at the end of the day, what you get, the wave function you get only depends on the particle coordinate difference. Up to a global phase, up to a phase. Okay. It's non-trivial. Yeah, it's non-trivial.
point. Okay.
Quick question actually about that slide that you just moved from. Yeah, this learnable embedding vector xi not equals e. Is e a function of ri?
No,
Oh,
no. There is
No.
just some random,
Yeah,
random.
E is the variational
variable.
parameters to be learned. Yeah, E is the variational parameter to be learned.
And it depends on I.
It don't. It
No,
didn't depend on
That's the
anything.
point,
No,
and that's the
no,
point
it's
I'm
in the-
making here. That's exactly the point I'm making here. You know, because if you start from this, it's highly non-trivial. At the end of the day, you can learn the non-interacting answer. The answer for non-interacting case should be yi equal xi. There's something special
Yeah.
about I, right? There's something special about I, but in here, nothing seems to depend on I.
Yes,
Right. Yeah.
that's a
So
good question.
that's the whole point of this discussion I'm raising.
very tricky. Yeah, very tricky.
Yeah. Okay, very tricky, right? Yeah. Okay, very
But
tricky.
then e, I guess, what does it depend on?
It's a
It's a
variational
random
parameter.
vector. It's a random
Variational
vector.
parameter. Yeah.
Yeah.
To be
It-
optimized.
yeah. It's yeah. It's
Be
a
optimized
random,
for each I.
It's initially random. It's initialized to be a random vector, and then they learn it.
They are the same for hi. Yeah,
I see. Oh, it's the same for each I. Okay.
yeah. They are
That's
the
why
same.
I'm saying that it's highly
No. Each I is random. It's randomly initialized for all the I's, and then after that they learn it.
They're using the same embedding vectors for all I.
Okay,
I
yeah.
see the implementation.
Oh, okay,
They
okay.
use the same.
I think all this is actually very dubious. You know, one has to think very carefully about all this stuff.
Yeah,
You know,
yeah.
I think my takeaway from this talk is that I do think that this Jastrow thing is the right thing. Okay. I think the Jastrow thing is a good thing, that you think of the many-body wave function as a reference state, which could be a simple state determinant times the Jastrow, right? I think that is a good thing. Okay, that is a good approach. But I think the implementation, okay, as you described so far, I think it's full of problems.
Yeah.
I think maybe that's why it leaves a lot of opportunity for us to make a contribution. Okay, and
Wait,
I
but-
think
Oh,
yeah.
In SciFormer, isn't it the same? What I remember from Google's paper is that it's also they only use RIJ as well, right?
No. Well,
They use RI.
I don't think there. Okay, first of all, I don't think there's a paper on SciFormer doing periodic boundary condition yet. They use the Ferminet.
Right, Ferminet is
And
only
they-
just RIJ, right?
In the Ferminet, they actually use both. I mean, I can probably just copy the paper in the chat right now. I just have. Yeah, this is their paper, I think. If you
No, but can you just highlight? I don't know. Can you just highlight that relevant what they used to set up their initial features?
Well, yeah, as in if you go to page 2, on the right, there's something, yeah. It says that they use both, basically. I mean,
But how do they use it? Let's see.
they did use sine and cosine, but I think the way they did it is they literally just put them in and then.
Wait, sorry, I'm just opening up the paper. Give me a minute. Okay, so I'm looking at the okay, maybe I should. I'm looking at the SciFormer paper. Maybe I shouldn't look at the SciFormer paper.
In PSI is based on one particle called feature, right? The input is one particle feature, Tony, right?
Yeah, the two particle features does not involve variational part, so it's only going in the Jastrow factor.
That's right. That's right. Yeah. In PSI, yeah. Oh, by the way, one thing I want to mention that related to what Tony said, nobody has used PSI for periodic systems in the published paper. And catch, there. Are you there, I was talking to Max yesterday because you were not available. You were not online. And I pointed out to Max, there's a big problem in his, at least in his implementation of Poisson formula for periodic uniform electron gas with periodic bounding condition. The Jastrow part is 1 over I minus Rj. But if you think about the catch on the torus, okay, with periodic bounding conditions, I minus Rj is
Yeah.
an illegal function. Okay.
Wait, they
Completely
wait,
illegal.
wait. They
Yeah, I pointed out to him, and he's just using R minus Rj, but this is a big problem. Okay,
Really?
is
It's not
know
translation invariant.
it's not it's not, it's meaning because imagine a system is from x equals 0 to L, right? Then if you have one particle near x equals 0, you have another particle near x equal L. If you use just xi minus xj, you will say the distance between the two particles is large. In reality, because it's periodic bounding condition, the distance between these two particles is actually small, not large. So all the stuff that you guys are doing with periodic bounding conditions using Poisson formula are wrong. Okay, are wrong.
But do you guys see some like gluing effect? Like as in just particle aggregating on the
Yeah, I mean, you have to be careful. You have to be very careful. You know, you have to be very, very careful. I'm not sure. At least, no. At least Max, the way Max told me that, at least in his case, he did not replace the Jastrow properly. You know,
But to
he
be
has this
fair,
Jastrow, which is still the 1 over I xi minus xj, which is not imperiodic.
I think
Yeah.
the main like repulsion between electrons or the main separation between electrons is given by the determinant. That's why we should be able to get reasonable results, but we should
Yeah, maybe the
we
result
should
is reasonable, but
rectify.
I'm saying that it is
Yeah.
certainly, the whole thing is incorrect.
Mhm.
It's really incorrect. It's a self-contradiction. You know, particles are in a periodic bounding condition, but you are essentially constructing wave function that is not periodic. Okay, the variational wave function is not periodic, so it's a big problem. Right.
Can they not just literally change Rij to sine Rij? Like, isn't it just
One
one line?
can do various things, of course. Yeah.
Yeah, I think that.
One can do various things, but all this needs to be done properly. Yeah. All this has to be done. You know, so you know, I think the what you guys should read is this deep solid paper, right? For example, the Baidang's people. I think they did everything properly. Yeah. Although they are not using Jastrow. Yeah. They're not using this this Jastrow factor. They're not using the Poisson formula. Yeah. So I'm saying that, yeah, basically, you know, if you want to use Poisson formula for systems with periodic bounding conditions, as Tony said, nobody has actually done anything, and and one has to think very carefully if you want to do it properly. Okay. Very non-trivial. So that's why, you know, Tony, right? That's a best decision we made is to use just to use disk. If we
No,
use
that's-
any other geometry, you know, it'll be
Yeah, but I
big.
think yeah, with magnetic field, it's like on torus, it's really hard. Yeah.
It's notorious, it's just notorious hard. But even without the magnetic field, the Poisson formula has not been implemented in periodic bounding conditions.
Yeah, it's quite surprising, but yeah.
Yeah, very good.
So wait, so it seems from the paper that both Fermi-Net and psi formula are open boundary conditions, right?
And the Fermi-Net has been implemented on periodic bounding conditions.
Yeah, I
Yeah,
mean,
but-
even the paper I
Oh,
just
really?
sent, there is periodic boundary condition, and I mean, basically, Deep Solid did something similar. They also did, yeah. periodic
Actually, who did it first? Is it Google? Did it?
Uh,
Is this before?
No,
or
Deep
after?
Solid did it a little bit earlier.
Oh, I see. Deep Solid did it earlier. I see. Yeah, then this Deep Solid is important work. Yeah. Yeah. Okay. Yeah. Okay. You know, I think, you know, maybe Tony. Yeah. In the interest of time, yeah. Can you quickly show us some results? Without. Yeah.
Wait, you mean
Not Tony,
the-
but
Jinze.
Jinze, can you quickly?
yeah.
Yeah, so I'll go into the experimental results. Yeah, so first of all, we play with some toy example with two particle Hamiltonian. Yeah, so the potential we use is a attraction potential with the particle distance less than a, which gives a weak attraction potential minus v naught. And if the distance is larger than a, there's no attractions. And we can transform this Hamiltonian in the center of mass coordinates so that we can rewrite the Hamiltonian into this form. And then we can
Actually,
use.
I think you can skip this part. It's like, you know,
Okay.
yeah,
It's
Yeah,
like,
yeah. Maybe in the interest
yeah,
of time,
let's
yeah,
just-
just
oh,
to
yeah,
show
just,
something out.
yeah. So the ambient NQS can solve the two particle wave function perfectly, and this is the density plot, and the density is symmetric about x equals to y. That means that this wave function is translational invariant. Yeah. And I try some fixed distance size with different particle numbers. And as the particle number is increased, the province is harder for MPNQS. And this is some fixed density cases. And I think in each case, MPNQS can solve this 1D system very well. And
But
this is
for the same problem I said earlier, right? Did you get the distance function properly?
yeah. I consider them on the torus. Yeah.
But did you? I mean, this is something we also discussed, right? Did you
Yeah.
get the? If one particle is near x equals 0, the other particle is near x equal L, the proper distance should be small instead of large. Did you?
Yeah.
yeah,
You just
we fixed
consider.
that. You fix that.
Yeah,
You
we
fix that.
fixed
You fix that.
We
Okay.
fix that. Yeah.
Okay. All right. Fix that. Okay. Good. Yeah. For
Yeah.
1D, okay. 2D and 2D also works.
Yeah, 2D works, and we haven't got a uniform charge density in this case. Yeah,
Yeah.
there's
This is
some.
also worrisome. If you don't get a uniform density, that always worries me. Yeah.
Yeah. And this is a density correlation we got from
Yeah.
these simulations. Yeah.
Okay. Sounds good. Yeah.
Yeah.
All right.
So that's all.
Thank you. Thank you so much.
Yeah.
Thank you. Yeah.
Thank you.
Thank you.
Thank you so much. Yeah.
Thank you.
Yeah. Actually, I think this the spirit of this Jastrow is really good. If you think about the even the Laughlin wave function for fractional quantum Hall, it can be written as a slit determinant times a complex Jastrow, right?
Yes.
Laughlin wave function zi minus zj to the third power times something, right? But then zi minus zj to the first power can be written in terms of determinant. Then the other remaining part, zi minus zj squared, that can be thought of as a Jastrow.
Yes.
Oh,
So
really?
I think these are
Okay.
all
Okay.
these are all extremely interesting, and I think but I think the current implementation of this idea in the literature is totally wrong, because I'm not convinced even for the non-entangling case it can work. One has to really think everything through carefully, right? So this gives a lot of opportunity for us to create something new. Okay. Yeah. Right. So
Yeah, good point. Okay.
yeah, so we should before doing anything, we should think about a good name, right? If we invent our new neural network, right, based on this idea. Yeah. I think the key is really a Y of X, right?
Yes.
Yeah.
Why don't we
Wow,
call it a
yeah.
propagator net? Propagator, right? Y of X is strongly based on the Green's function G of X prime, right? It's some kind of a propagator or some kind of a one needs to one need a new name first. Yeah, Y of X. I like this idea a lot. That the neural network is used to generate Y of X.
Right.
Yes.
It's really kind of a configuration transformation, right? X is a configuration and Y is another configuration, right?
Yeah.
It's really transformer, but transformer the name has been used. So let's think about a new name.
The name is Backflow.
Huh?
The name is
No,
Backflow.
but that's just a boring name, right? Let's give it a better name.
that is the
No.
that's the
Such a
existing
boring
name.
No, Backflow. No, that's just a horrible name. We're talking about neural network, right? We're not talking about this particular Y of X. It's part of a neural network, and we should give a name.
Yeah, but the general idea of a Y of X is a backflow.
Fine. But that's not the point. That's not the point, okay? Right? I mean, backflow is the idea. It goes back to Feynman, okay? Right? Why don't we call it Feynman net? No, nonsense. All right, let's just think about a good name. Right? I mean, this backflow idea is too limited, right? This backflow, what I mean is its name is too limited because it originally was introduced for the superfluid, right? But I mean, look here, it's really, yeah. But you see what I'm saying, Aiden? The thing about the Laughlin wave function can also be written this way: Z minus GS squared. That has nothing to do with backflow, a liquid, nearby coordinates are transformed. Z minus GS squared, it actually completely
Yeah,
changes.
but that's just a pure Jastrow. It's not a Jastrow backflow wave function. It's just a Jastrow wave function.
Especially, sure.
Well-
But again, anyway, we have to think about a good name. Yeah, it's really a mapping from X to Y. Right? The most general, it's really a transformation. Right? It's really a configuration transformation. Right? What should be a good name for this configuration transformation? For any configuration X, you want to generate a corresponding Y, and its permutation
Oh.
symmetric. Yeah, I think it's much more general than the original backflow idea that was considered in the literature in the superfluid helium, because there, it's all short range correlation that matters. But if you think about most general wave function, it's long range. It's completely non-local, long ranged, right? Oh, what is this?
Confinement.
Transformer. No, let's not bring in Feynman. Yeah, this is totally new, right? It's really a set of a coordinate transformation. It's non-local.
Some
It's
sort of
non-local.
correlated coordinate or correlated some sort of correlated coordinate system transformation or something like that.
Yeah, but my point is it's not local. It's not local.
Yeah.
Yeah, it's not
Graph
local.
flow.
A what?
Graph flow.
Graph flow, fantastic, right? But it's really, but more specifically in the physics context, in terms of many particle configuration, right? It's really the mapping, transformation of configuration, right? That preserves permutation symmetry, right? But why call it flow? Why? It's a mapping, right? It's a permutation
Correlated
variant.
configuration transformation.
Again,
Mm.
what?
I don't think this is good, but correlated configuration transformation.
No, that's too long, right?
Just brainstorming. It's not
Yeah.
good, yeah.
Just to be catchy.
Yeah, we need something catchy. Exactly, that's a good name. Yeah, before you do anything, you have to name. Yeah. What should we call it? I mean, what's the synonym to transformation? Transformation. Maybe someone can ask ChatGPT. Yeah, transformation. Some sort of a transformation, right?
Map.
Map.
Morph is like
Yeah, I was gonna say morph. Yeah,
Yeah.
thinking about morph. Yeah, but a morph somehow.
It's morph is not, it doesn't have a morph doesn't have a sunny enough or yeah, morph is a bit
Morph doesn't sound very bright. It sounds
right.
very.
Doesn't sound very
Yeah, it sounds very dark. Right. Yeah, some sort of a transformation. Yeah, it's really a configuration transformation. Yeah, right. For any X, it generates a Y. Yeah. We have to think about this. Okay. Maybe we don't know the right away, but yeah. But I think this is a very promising thing, but I think the current implementation is totally wrong, in my opinion. In fact, I can prove it's wrong. Okay. Think of this following way. Even if you have a translation invariant system, okay, the wave function could depend on the center mass momentum. Okay. Center mass coordinate position x1 plus x2 plus x3 plus xn. Because the ground set can carry finite many-body momentum. The many-body momentum is e to the I q times x1 plus x2 plus xn, right? You see, this immediately tells you that the many-body wave function not only depends on the difference between particle coordinates, but it can also depends on the center mass position. Okay, it can depend on a particular way, which is e to the I q dot x1 plus x2 plus xn. Okay, right? So the current implementation is full of problems. It's totally wrong, right? So I think one has to think about how to do it properly. Yeah. Right.
Okay.
Make sense?
So-
Okay.
Yeah, sounds
Yeah.
good. Okay.
I think it's a lot of fun. Yeah. I mean, yeah, it's a lot of fun. Yeah. Okay. Why don't we continue all think about this?
Could I
Sounds
ask
good.
a
Okay.
question?
Yeah.
I had a question actually about the slides, but is that all right?
Okay. I can share this again.
Yeah, could you go to the slide right before you started talking about attention? I just want to understand the relationship between the graph part and the attention part.
Which parts?
I think right before you started talking about attention.
Yeah.
Oh yeah, the last
Yeah.
Oh yeah,
So-
this
yeah. So the attention is used to construct this message function for yeah. So the relationship between the attention and message passing neural network is we use the attention layers to construct this message function. Yeah.
I see. So is the message function just an attention layer?
It
I think
doesn't.
I think attention, if I understand correctly, attention layer is used to generate this message function.
Yeah.
Is it correct?
Yes.
Attention layers are used to generate the message function.
Yes.
Like multiple attention layers?
Well,
Yeah.
I don't
They.
No, just one. It's just one per layer.
So is it correct to say that like the message function is an attention layer?
Yeah, you can use
yeah.
another kinds of neural network, but in this case, we use the attention layers as a message function. Yeah.
Okay, and then where does the graph? There's a disconnect in my understanding between the graph and the attention.
In graph,
Yeah.
basically, by
Yeah, so-
graph, I think what Junzi means that it's a structure that has nodes and edges. And
Yes.
this particular structure satisfies permutation equivariance. That's what we need to generate y as a function of x.
Yeah.
Does it make sense, Aiden?
Yeah, you can think of the features of the features of electrons as a nodes and their difference, their coordinate difference and their spin products as the feature of the edge. And you can think of the graph is a auto connect vertices between vertices. And so we didn't specify the adjacency matrix since all the vertices are connected to each other. Yeah. So we don't explicitly write out the adjacency matrix. So you will feel that.
Oh, okay, because
yeah.
Okay, so is it correct to say that like the information, the input to this neural network is just the information contained in the graph?
Of course.
Yeah.
That's the whole point. Input.
Yeah.
Input feature.
But
That's
then-
what is the initial feature.
If the graph is all to all, so the graph itself is the input feature.
Of course.
Okay, so
Graph means
but
that
then if it's all to all,
with nodes and link and edges. Okay, with nodes and edges, and each nodes and edges have the corresponding vectors associated with to them. And the initial features Junzi talked about, this xi is learnable parameters, and xij is those things that he just listed. Those are all the inputs. Yeah. Basically, to any neural network.
yeah, but what is the? I mean, I got that, but what is the relationship between that slide and a graph?
I mean, that whole thing is
There was the slide where
through a graph, because a graph consists of n nodes, right? Each node contains the particle information, or each edge contains information between the two particles, xi minus xj, that kind of information.
yeah. So in that slide, the xi knots are the nodes, and the xij
Yeah, are the edges.
uh,
Are the edges.
are the edges.
Yeah, yeah.
Okay.
Graph is just a particular layer structure, right? The structure of each layer. Yeah, instead of an order
Or is it the
list
structure of
of each layer.
Wait, isn't the graph here like how you pass from one layer to another? I thought
No,
with
I was
layer you
no,
just
I was thinking as
attach-
more like a
No,
layer.
no. Yeah.
Each graph, each layer, right? And then
Yeah, but you can also, I mean, it's also correct to say that it's how you pass, how you update from one layer to the next, because you are, but I would prefer to think of it as the structure in each layer, and then use the structure in
Yeah.
each layer
to
right,
update.
to construct the messages and to update.
Yeah, exactly. Yeah, fully agree. Yeah. Wonderful. Yeah. So yeah,
I mean,
no,
it
I think
seems to me like that's just attention. It seems to me like the graph is how basically the initial physical inputs, the coordinates and spins of all the particles, is input as into the neural network, which is
no, but the graph is keep getting updated, right? So from layer to layer, there are many
yeah. Well,
layers.
that's just like saying the information, like
The graph is keeping being updated. Each layer is a graph
the graph gets
updated. Yeah. So that's like saying that go from one layer to next layer to next layer, etc., etc. Yeah.
yeah. Okay. I mean, yes, the graph is like the piece of information that the neural network
Yeah.
is updating.
Okay.
and
At this point,
operating on.
yeah. To get in the bottom of all this, I strongly encourage all of you, all of you to think about actually implementing it. Actually implementing it. Yeah.
Hands on.
Yeah. So I actually think this idea of using this YLVAX, right? I think it's a brilliant idea. Combining with neural network is very promising, and yeah, I think it's a great thing. But I think current implementation in the literature is completely incorrect. Yeah, in my opinion, it's completely incorrect. Especially this initial input, which says that Xi cannot contain any information about the particles. It only contains just learnable parameters. That is totally incorrect. It's totally incorrect. Okay.
Yeah.
Okay. Yeah, we can chat more, Junzi and Zhen, offline, and give me some
sure.
idea what
Yeah.
we should do next. Okay,
Yeah.
sounds good. So let's see. We need our weekly group meeting will be on Wednesday. On Wednesday, 1:30. This week is a bit special, and so we need volunteers, right? We need volunteers. Please think about it. If you want to give a talk, yeah. Sounds good.
Sounds good.
Yeah, I
Okay.
can do next week.
Okay,
As we talked
fantastic.
about.
Thank you so much,
Yeah.
Lena. Yeah. What are you going to talk about?
This superconducting devices with like diodes and superconducting magnets.
Yeah, perfect. Yeah,
Yeah.
wonderful. Okay. Okay, great. Yeah. Okay. Happy New Year again. Yeah. So
Okay.
you and I, we should stay online. Yeah. All right.
Okay. We'll stay online.
Okay. Bye. Yeah. So Hugo, we need to go to another meeting, which I haven't arranged. Let